Before we start our conversation about the law of Sine's ambiguous case, we really need to define and remember what an altitude of a triangle is. Now you may ask, well, why is that important? When we get to the video on the law of Sine's ambiguous case, it all has to do with altitude. So I like to stop and just find area of an oblique triangle by finding the altitude. The reason that's important is in a right triangle, the area is equal to 1/2 base times height. Well, the height is actually an altitude, which in a right triangle doesn't matter because the height that you see at the right angle is the altitude and it's just given to you, or maybe you have to solve for it. But in an oblique triangle, you have to find it using trig. So the formula actually comes out the area is 1/2 base times the altitude. And I'll show you how we get this trig here. So what is an altitude? Just to remind you, an altitude of a triangle is a line segment through the vertex, any vertex, and perpendicular to a line containing a base, any base. So I'm just going to draw it right here. This will be my altitude. And that altitude, again, is specific to this base. There are two other altitudes. I mean, technically, you can have an altitude here and there. When I do an example, I'll show you, you come out to the same answer. And so just looking at this problem, if I want to know what this altitude is, I've actually formed a hypotenuse here. Now keep in mind that that hypotenuse is not, let's label the triangle, make it a little clearer. We'll call this angle A. We'll call this angle B just because it matches the base, and we'll call this angle C. So even though this hypotenuse is side C of the outside triangle, it is the hypotenuse of the triangle I drew inside of that triangle to form the altitude. It's the hypotenuse of this triangle right here, which happens to be side C. Okay, let's glue all that together. Using regular trigonometry, right angle trigonometry, because I have a right angle, this altitude is really opposite, okay? And this, of course, is the hypotenuse. So we're talking about sine here. So sine of A will, of course, be opposite over hypotenuse, but labeling it the way we did in this triangle, it's really the altitude over the hypotenuse. And if I want to solve for the altitude, because that's the whole point of the problem, I would multiply by the hypotenuse, getting rid of the denominator, giving me altitude. And so the altitude will come out to hypotenuse times sine of angle A. Well, as we labeled earlier, the hypotenuse is the hypotenuse of the inner triangle, but it's also side C. So the altitude or height of the triangle is always equal to little c sine A. And keep in mind, I did set up the triangle so that we're talking about this triangle. We could have done this one. It gets a little confusing. I like to stick to the left side of a triangle. It makes everything a little clearer for this and the law of sines notes. Now, so once I do all that and make that, everything connected, that hypotenuse is really C of the outer triangle, you can see that the area is 1/2 base times C sine A if you draw the triangle so that the angle you're looking at is in the left corner, which I always do. I'm very consistent about that. It was the key as a student to make this make more sense to me. All right, we'll look at some examples and we'll actually get some areas, and then we'll move on to the law of sines ambiguous case. When looking at these examples of area with oblique triangles, you have to be careful about where you think the altitude is. The most obvious place for the altitude in this problem is here, drawing from this vertex to this side at a 90-degree angle, making it the base. But there is another altitude that we'll look at that will actually produce the same answer. So let's just start with the basic problem. The idea here is that in order to find the area of a triangle, you have learned in the past that the area is 1/2 base times height, which is correct. But that height is the side of a right triangle, and you typically learn area before you learn about trigonometry. And so the actual formula that's needed is 1/2 base times the altitude, and the altitude is, of course, the height of the triangle. But if you've ever wondered why you never saw this in geometry, you learn about right angle trigonometry after you learn about these formulas, and typically you don't return to the formula because it's something you've been seeing since middle school. So we're going to look at it now in preparation for the law of sines ambiguous case, because it's critical for the law of sines ambiguous case. So trying to find this altitude right here, you notice that we have this angle here that we could use, and this would be actually the opposite in the normal right angle SOHCAHTOA trig. This would be the hypotenuse. And again, we're talking about a triangle that's an interior triangle to the actual triangle we're trying to find the area for, because the outside triangle, right, is not relevant to trying to find the altitude other than using its side, which is actually the hypotenuse to this interior angle that I drew. So to find that altitude, what we're going to do, we're going to call this altitude number 1, because we're going to come back and look at a second one in this triangle in just a couple of minutes, is we would do sine of 40 degrees, and that would be, of course, equal to opposite over hypotenuse, because that's what sine is defined as a ratio. And so that would be altitude, and in this example, divided by 5. And to solve for this first altitude, we're going to multiply both sides by 5 using our basic algebra skills, giving us our first altitude is this, right? So my altitude would be 5 sine of 40 degrees. And what that means is this altitude is locked into this base, which we will call base number 1. So, and this is all you have to do the problem. I just want to show you that it could be done in a different ratio. So for this first problem, the area would be 1/2 of the base, which is 10, and then times the altitude, which is 5 sine 40. And you may say, isn't that a decimal? I just like to go ahead and put it all together so it's a little more obvious what I did, and then I'll type it in the calculator. As you can see, I did it right here to get that the area of the triangle is actually 16.070 if I round up to 3 decimal places. This 6 would round, this 9 would round the 6 to a 7, which would round that up to 70. And this would be inches squared, because you have to include units. Very important in a trig problem to include units. So why did I call this base 1? You could also find 2 other altitudes. I'm going to just do this one because it has a value at the base, and I'll do a separate example of what would happen if we couldn't do a base. What would I do if I try to pick that as the base, which you could. But right now I just want to show you that the area will be the same for both. So when I look at this triangle, which is now here, right, this now becomes the other base. This is base 2. And what happens is I still get to use 40, but using right angle trig, the altitude here would make this its hypotenuse. So let's take a look at finding altitude number 2. This is just for fun. We already have the answer right here. So if you understand that and you could just move forward to the next problem. But I want to show you that the altitude, the second altitude will give you the same answer. It's just interesting if you like math. So in this example, we're going to use sine of 40 altitude over 10. So sine of 40 is equal to the opposite, the altitude, divided by the hypotenuse, which I labeled right here, which would be 10. So the altitude in this problem is going to be 10 sine 40, right? And just multiply by 10 on both sides. That's how I got the answer, in case you were curious. And so to find it the second way, the area would still be 1/2 base times height, which is the altitude. But as you can see, I relabeled it. This is now my base number 2. So it'd be 1/2 5 times the altitude, which is now 10 sine 40. And when I type that into the calculator, I get the exact same thing I got earlier. So that's really cool, right? 5, 10 sine 40 is the same as the other one. It is finding the area of the same triangle. So if you really want to strengthen your skills, why not try to see if it worked from a different perspective? Very important as we move forward that these answers are the same. Even though I use a different altitude, it is the same triangle. So what happens if I don't know a side? Let's take a look at a second example for that. So let's say this was the problem we wanted to do. They only gave me one side. So let's just make the easiest base we can here. In my opinion, the easiest base would probably be to draw the altitude here. Try to make it a little bit more right angle-ish. It's kind of hard to do because you'll see why in just a second. That it's very close to being 90 anyway, but it's not 90, so we have to find this altitude. So to do this problem, we're going to again have to label this the altitude, and we're going to need to find opposite. And so the first thing we realize is that we got to use the Angle Sum Theorem to find this. And this starts to feel like the problems that it's meant for, which is law of sines. So the Angle Sum Theorem says take 180 degrees, subtract out the other angles that you're given, and that will tell you that that angle is 100 degrees. And so you can see, well, it was kind of hard to draw that altitude because it's close to 90, which would have made it that side. And so even after you do that, you realize, okay, that's great and all, but what's my base? So we got to stop for a minute and remember, the whole point of all the stuff that we're doing here is to find something eventually to do with the law of sines. And it's very relevant because to find this base, which I don't know what this base is, I'm going to have to use the law of sines. I'm going to use my key ratio of 8 over sine of 30, or sine of 30 over 8, however you want to do it. And then I'm going to set that equal to the base, which is actually little x, right? So it's x according to this triangle, and then divided by sine of 50. So I did that here. The key ratio, as I mentioned, 8 over sine of 30 is equal to x over sine of 50. You, of course, then cross multiply, giving you x sine 30 equals 8 sine 50, and then divide. So you get 8 is equal to 8 sine 50 divided by sine 30. Type that into a calculator, and you get that this base is actually equal to 12.257. And you had to calculate it because you didn't know what it was, right? So just type that in there and got the answer. And so now that I have all my missing pieces, I can find the area. I still need to find the altitude, but I do know the b. I did that one first, and now I'm going to find the height. So the area is 1/2 of 12.257, and then yet to be determined. We'll determine that in just a moment. So to do this one, we'll do the same thing we've been doing, which is the altitude is going to be found by doing sine of this angle that I just found from the Angle Sum Theorem is equal to altitude divided by the hypotenuse, which in this triangle here, I'll go ahead and color code it. This is my little tiny sliver triangle here. That's the interior triangle to find the altitude. So it would be opposite over hypotenuse, which would be 8. And then I multiply both sides by 8 to get my altitude. And that's what I'm going to go back and put in the formula. So some students will say, how do I know what I need to do? Here's my advice. Define a base and then see if you can define a base on a number that exists on the triangle. In this particular problem, that wasn't possible, right? There was no way to define. I mean, I guess I could have drawn it upside down. So there is a way to have done it that way, but I just wanted to give you a different perspective. But, you would have still had to do the Angle Sum Theorem, and then you maybe had to rotate the triangle. So I went ahead and did it this way to show you that it was possible. Maybe unnecessary, to be honest with you, right? So some of you may have been watching this example and said, well, why didn't you just call 8 the base? I mean, I could have, but I was trying to also, give you some connections to the second part of this lesson, which is the law of sines and the ambiguous case, which you do in comparison to its angles and sides. All right, so let's go ahead and just find that answer in Desmos. So we're just going to type in 1/2 12.257 times 8 sine 100, which if we type in the Desmos, making sure that it's in degree mode, comes out to 48.279. And that, of course, would be in feet squared, because we're talking about area. All right, so now that we've learned how to do altitude and learned how to do something with it, we're now going to move on to the law of sines ambiguous case. There are many cases to the ambiguous case of the law of sines. First, what is the ambiguous case of the law of sines? If you are given two sides followed by an angle, that is what's considered the ambiguous case. In the ambiguous case, the first example, which I think is the easiest to understand, is when you have no triangle. And that occurs when the contained side is less than the altitude, or the side opposite of the angle given. is less than the altitude. Please understand that the altitude is b sine a, which I did several problems explaining that with area, so you might want to watch that video before you watch anything about the law of sines to understand what an altitude is. And keep in mind that the contained side does not have to be a, and this a does not have to be a. I mean, this could be x, and then this would be, the contained side would be x, and the altitude would then be x. So my advice is to understand what an altitude is, what an opposite side is, what a contained side is. But if that contained side is less than the altitude, you have no triangle. And the reason is, I mean, think about if you ever, when you were a kid, and you try to make a fort out of blankets, and maybe a couch or something, if you tried to put a pole in that fort and it was too tall, then the fort wouldn't work because the altitude or the height was too tall. So let's look at an example with actual numbers in it, an actual algebra. The example, visually makes sense because your altitude is just swinging right here. You have a swinging altitude and it never hits the ground. It's just kind of, where do I go? And so to look at this algebraically, what we're going to do is draw a triangle with A being 7, B being 9, and the angle being 54. Now, I want to remind you again, if this was side M and this was side angle M, I would draw this exactly the same way. I'm just labeling it, and that's what I meant by you really want to figure out what I'm talking about contained side and angle. So looking at this picture, you have the 54 on the left. I always draw it on the left no matter what the labeling of the triangle is. Across from that is 7. And then B, whatever this is. Again, this doesn't have to be B. This could be the side O. I still would put it here. I always draw the picture the same way to keep it in perspective. And so my altitude is always just drawn to this bottom base down here. And this base is not needed to be found right now. I just need to know what the altitude is. So the altitude would be, using the triangle that you see inside of the triangle, the interior triangle, would be opposite of hypotenuse, or altitude over 9. And so sine of 54, opposite of hypotenuse, would be altitude over 9. I would solve this by multiplying both sides by 9, just as we did earlier. And again, I'm going to remind you, you're going to want to watch those area videos, because I assume that you have, looking at this. And our altitude is 9 sine 54. After you solve that, which comes out to 7.281. Well, 7.281 is greater than this opposite side, and that's the problem, right? If the contained side is smaller than the altitude, you have no triangle. You just stop and you write it down that there's no triangle. Well, let's say you missed that. If you try to do this problem anyway, the calculator would say undefined. It's good not to waste your time and type it into the calculator, but this is almost a no-lose situation, because even if you don't know this and you try to type it into the calculator and try to actually do the problem using the law of sines, using the key ratio of 7 divided by sine of 54, and then you try to find any of these other angles, it will say error, undefined, or it might say error domain or something. But this is the reason why, because the contained side, the side opposite of the given angle, how about we say it like that, is less than the altitude found by doing the regular right angle trig of that interior triangle. So here's the second example. Well, what happens if you do have a triangle and it's actually a right triangle, meaning you don't even need the law of sines, which is really, really important. So what I'm talking about visually here is, what if this altitude, which you don't know where it is, it swings in and hits at one exact spot, and that spot is right. And so you don't know if this visual is happening until you look at that contained side and what its comparison is to the altitude. So notice in this problem, I mixed up the labeling. I labeled it B. B, in this diagram that you're looking at, this would be B. The contained side would be here. The altitude, which we don't know is the altitude, would be here. And then this would be whatever it is. I labeled it A just to make sure kids could label it correctly. But you don't really need to worry about what any of this is labeled. You need to worry about putting this angle on the left, whatever's across from it, and whatever you have left, put it above it in between those two things, so that you have side, and then angle. Again, that's what's critical. So let's take a look at this particular drawing with this information. So what I did in this problem is I put that B right there, put the 30 there, opposite of it is the 5, and then between those would be 10. Again, side, angle. And I found the altitude the way you've been used to finding altitudes, by doing sine is opposite of hypotenuse, so sine is altitude over 10. Then, of course, you solve this by just multiplying by 10. And again, if you have been doing this since the beginning of the assignment with area of triangles, this becomes pretty routine. And so altitude is 10 sine 30. So then we have to realize then that the altitude is equal to 5. You can type it in the calculator, 10 sine of 30 is 5. And the first analogy is, okay, well, that altitude is exactly the same as the contained side. It's not less than, it's not equal, it's not greater than, it is equal to. And this means that we just have a leg of a right triangle. The altitude is actually the leg of a right triangle. We had no idea, and so when we just redraw it, what we're going to do is we're going to take this picture that we drew, which was the wrong drawing, but we didn't know, and we redraw it with that being right there. So this picture was off. It's actually, that 5 is there. So we just redraw the picture with the 5 being the side of the right triangle, finding this angle C by doing the Angle Sum Theorem, getting 60 degrees. And after we redraw that, if I want to solve the triangle, it's pretty easy to do. Remember, if you have no triangle, you're done. But if you have a right triangle or any other example, you have to actually do the problem. So now we're just going to go back to the very beginning of what we learned in trig. If I want to find, I'm going to write down what we have. We have angle B is 30 degrees. We know that angle A is 90 because it's a right triangle, because we discovered that through the altitude. We used the Angle Sum Theorem and subtracted to get that the other angle was 60. Then we were also given A and B were 10 and 5, so the only thing we have to find is side C. There's a lot of ways to do it. I'm going to use 30 in the given information, just in case I did anything wrong. So with the given information, this is opposite, and this would actually be adjacent, right? So I'm going to do opposite over adjacent, which is tangent. Tangent of 5 over C, you would just simply multiply both sides by C, giving you C tangent 30 is 5. You would then divide by tangent of 30. Remember your algebra skills in trig. And then you get the only answer you actually had to find using trig in this problem, which is 5 over tan 30, which if you type in the calculator is 8.600. Then double check to see if there's any units, which in this problem there were not. So we can leave it like that. So just a recap, you don't know what you get with side angle. We were given at the beginning side angle. You don't know what you get, so you have to find the altitude and then reevaluate what you think you have from there. And then once I realized in this case that I had the altitude as actually the side, they're equal, then I drew a right triangle and corrected my mistake that I didn't know that I had until at that point. And then I put in what was given, and then I found the only side missing, which was C, using just regular right angle trig. Because in this problem, it was a right triangle. And now we're going to look at what happens if we have the ambiguous case where we have a side, and an angle. And that particular case makes an oblique triangle where we actually use the law of sines. So keep in mind, to review, we looked at what happens if the altitude was too small. It doesn't make a triangle. We looked at what happens if the altitude is actually a side of a right triangle. When that actually, you figure out the altitude, it's actually what you were given to begin with. And now we're going to look at what happens if the side is long enough that it swings and hits the ground, forming a oblique triangle with an altitude, like you're used to seeing with the law of sines or an area problem. Now this will happen when the contained side is bigger than the altitude, creating a triangle, but then the contained side is then greater than the hypotenuse of the interior triangle you use to find the altitude. Now, that may sound complicated, so let's look at an example of what I'm talking about. So here we have C, B, and angle C. Remember that you're not going to have A, like in this diagram, you're going to have whatever they give you. So put this angle in the lower left, put this across from it, and put this between the two so that you get side angle. And so, very routine picture here that we've seen many times. To find the altitude, we're going to do sine of 85 is equal to altitude over 6. And we're going to do this to determine, is there a triangle to begin with? So sine of 85 is equal to opposite over hypotenuse, altitude over 6. And then we solve this, as we've been doing, by multiplying by 6 on both sides, giving us that the altitude is 6 sine 85, and we type it in the calculator and we get 5.977. Now that number confirms that yes, there's a triangle. Why? The altitude is smaller than 11. Remember, if the altitude is too big, this will hang up. If this was 11.1, this could not hit the ground. But if this number is smaller than 11, even if it were 10.9, we would be good. So we're good. We have a triangle. So now the question is that triangle right or oblique? And the way you determine that is you look at the contained side, and if the contained side is bigger than the adjacent side, or the side you use as the hypotenuse, I think in the original directions it said the hypotenuse of the interior, or you could think of it as the adjacent to this side. So if this number right here is bigger than this number, then you have an oblique triangle, one of them. If they're, and so that oblique triangle is just one triangle that you're used to seeing. It's this picture that you actually drew. So what happens next will be the longer two problem example. So let's just solve this problem. Again, if you don't have a triangle, you're done. If you have a right triangle, you use sine, cosine, or tangent. If you have one oblique triangle because your contained side is bigger than your adjacent side with the altitude within the tolerances of the triangle existing, then you just do a regular old problem with a key ratio. Key ratio would be 11 divided by sine of 85, set equal to 6 divided by sine of b. You're going to cross multiply, okay? 11 sine b is equal to 6 sine 85. You're going to divide by 11. You're going to type it into the calculator, okay? But you can't quite finish that until you solve for b. So you're going to have to inverse sine like we have done way back in the regular normal trigonometry problems, the right angle trig. You can't type this in the calculator. It'll give you a decimal. You got to type it in after you've solved for b. So b is going to be inverse sine of 6 sine 85 divided by 11, which is 32.19 degrees. Okay, so the next step would be, let's see what we have, because we found that angle. We were given C, B, and in the original problem, side C, angle C, and side B. We just found B by using the law of sines. We find A by using the Angle Sum Theorem. And the only thing left is to then find this side. And we're going to have to just go back and say, well, how would we do that? You can relabel the triangle if you want, or you can realize that we're doing the law of sines. So we're going to use the key ratio. Key ratio is going to equal A, and then divided by sine of this angle I just found from the Angle Sum Theorem. And so then I cross multiply, okay, giving me A sine 85 is equal to 11 sine 62.086. Then I divide by sine of 85 on both sides, and that I can just type into the calculator as I normally have. And that'll give me my little A that you saw up there. That gives me that number. That's how I got it. So another thing to remember is that's a lot of jumping around. You might just want to, in your calculator, start labeling things. So when I found that ratio, I found that ratio to be B. So I went ahead and stored it as B. And then I went ahead and did 180 minus 85 minus B. You do that by hitting the store button on your calculator. Just as a reminder, the store button on the TI is right here. It's similar on the Casio, it just has an arrow. And so, again, I stored that as B. I did 180 minus 85 to give an angle minus B. And you can just see everything on the screen, which is beautiful. Then I stored that as A, right? So I stored that as A. And then I was able to calculate this piece by just typing in sine of A, 11 sine of A divided by 85. And you can also do that on Desmos, which is even more convenient because you can just copy and paste like you normally would. So you can see I typed that in, make sure it's in degree mode. I then said B equals this. I copied it. I did 180 minus 85 minus B. And then I stored that as A by saying A equals. And you can even use an upper and lower case in Desmos, which is great. And then I did 11 sine A divided by sine of 85 to get that 9.757 as the other side. Now, very important, students will say, why did you have an inverse sine here and not have one here? Remember in the calculations that the first thing we were doing is trying to find an angle. See how we were trying to find capital B? So you knew you'd have to use an inverse sine from way back when we learned about right angle trig. We're down here, we're finding lowercase a, so I don't need that inverse. All right, next up is the two triangle example. So now we come to the notorious two-triangle law of sines example. And like most things in math, when something that seems complicated, let's just start with something we understand and have done a lot of, and that is finding the contained side across from the angle that's given, and then comparing that to the altitude. Now, if the contained side that is across from the given angle is greater than the altitude, then you have a triangle, which makes sense. Otherwise, your altitude's too tall. This thing is just hanging around it. It can't hit the ground. And so to have two triangles, that contained side would have to then be less than the hypotenuse of this interior triangle that you use to find the altitude, meaning this one. Some people will say, is A less than the adjacent side, because it is side angle. There's only one more side, so they just call it the adjacent. But that's what we're looking for. We're looking for a triangle that exists such that this side is smaller than that side. Now, visually, the reason this happens is, if you have a triangle that exists, then the side will hit the ground here, forming your just classic oblique triangle. But if it's just right, it'll go through here, pick it back up, it'll fit right in there, making this little sliver triangle. So let's take a look at actual numbers here. Let's get some concrete information. So we have a side A that's across from the given, meaning making it the contained, and then another side. Always draw this as side angle. That's the whole point. That's the ambiguous case. And so we have this classic example that we've seen several times. And the altitude in this interior triangle, the altitude is opposite over hypotenuse or sine. So sine of 25 would be altitude over 9. You multiply 9 on both sides, you get the altitude as 9 sine 25, which comes out to 3.804. And that number is smaller than 5, making a triangle. Otherwise, if the altitude were too large and that were 5, then it would look like that. It wouldn't touch the ground. So the first piece of analysis is always, do you have a triangle? And the answer in this case is yes, I have a triangle. Then you move on to how many there are. So how many triangles are there? Well, if you look at the contained side, it is smaller than the hypotenuse of that interior triangle, otherwise known as the adjacent. 5 is smaller than 9, making a triangle right there, as well as the one you see. And so that's how we get two triangles. Now, again, in the idea of just, not freaking out about math, the first example is just the one you're seeing here, right? I have a key ratio of 5 divided by sine of 25. I'm going to set that equal to this side, which is this angle, which is across from side B. So I'll call that B. I'm just going to do the same thing I have been doing, right? So take this triangle, set up my key ratio, 5 divided by sine of 25 is equal to 9 divided by sine of B. I'm going to cross multiply, and I'll get 5 sine B of 9 sine 25. I'm going to solve for sine B by dividing by 5. Keep in mind, since I'm finding an angle, I have to inverse sine, just like you did, back when you were doing regular right angle, SOHCAHTOA, sine, cosine, tangent trig. If you need to find an angle, you have to use inverse sine. So you inverse sine this ratio, B is inverse sine of that ratio, and you get this first angle. Now that angle is the key to the second triangle as well, which we'll talk about in just a couple of moments. So what do I do once I get B? Once I have B, to find C, I'm going to use angle sum. So to find C, I use angle sum. I take 180 degrees, subtract the given 25, subtract the just found 49.57527, giving me this 105.7473, which is clearly obtuse, which makes sense. Make sure what you're doing, that's an obtuse angle, so that's an obtuse value. Make sure what you're doing makes sense as you're going along, so you don't get overwhelmed. I'm going to go back to this key ratio and use it again to find side C. So 5 over sine of 25 is equal to side C divided by sine of the angle I just found that corresponds to side C. I cross multiply, giving me C sine 25 equals 5 sine 105.473. And I divide by sine of 25. I do not need to use inverse because I'm finding a side. Remember, sides use sine and cosine and tangent. Angles use inverse sine, inverse cosine, inverse tangent. And so I type that into the calculator and I get 11.402. Could, of course, done all that on Desmos as well, or Casio, or what have you. So now I just write out what the first triangle is. I was given 25 degrees. That was directly across from the side A, which was 5. I was also given 9. I found 49.527 using the law of sines. I then found 105.473 using the Angle Sum Theorem. And then I used the Angle Sum Theorem right here to find side C with the law of sines. Then I got 11.402. So triangle 1, same boring law of sines stuff that you've always been doing. So now how do I find the second triangle? So what happens is, in the first triangle, I could have drawn, right, here's my first triangle, I could have drawn that 5 right over here instead, right? So that 5 could have been there. I chose to draw this larger triangle, but doesn't this triangle right here meet all of the characteristics that I was given, right? This has a 25 degrees, it has a side that's 5, it has a B that's 9. That little triangle meets all the characteristics, and it's possible based on this analysis that we did here. So what do? Well, I don't just use the same key ratio to find B. I will use it later, but I don't use it to find angle B, because if I use it to find angle B, I'm going to get the same result. What I do is I have to understand that this triangle here is key to understanding how to find the new little triangle that I've drawn now over here. So how do I do it? Well, what I do is I take this angle and I realize that I actually have an isosceles triangle. I have this is equal to this, and we learn in geometry that that means, okay, that this angle is also here. So all of this is outside of this little triangle, but is key to finding this angle right here. Like, how do I find that angle? I now have a linear pair, and that linear pair has 49.527 from the previous problem that came from it being isosceles. So how do I find this angle? I don't use trig, I actually use geometry. And remember, geometry is the study of shapes. And so when you look at this, all of this up here, other than this piece to find the altitude, it's really the study of what kind of shape we have. So to find this new B here, to find new B, what I do is I actually use the linear pair, that it's actually 180 minus the one I found earlier. So new B is found by taking 180 degrees minus old B from geometry and linear pairs. I just take 180 and I subtract 49.527 from over here, and I get that new B is 130.473 degrees. Well, that's important to understand. That's the critical piece. Notice that it is obtuse, and that's obtuse. So it does all kind of fit into, the pieces fit in where they should. At that point, once I understand that this is not trig, that it's geometry, every piece of it from this point is identical to over here using new numbers. What did I do after I found this 49.527? I used the Angle Sum Theorem. I'm going to do that again, but now I'm going to do it with this number. So I take 180, I subtract the given 25, I subtract 130.473, and that gives me that new C, right? We'll call this new C. New C is 24.527 degrees. I then look here what I did here. I used a key ratio. I found little c. I'm going to do the exact same thing. Key ratio, find little c, but I'm using my new c to do it with. So then I cross multiply. I get 5 sine 24.527 degrees. I cross multiply. That gives me c sine 25. I then divide by 25 on sine of 25 on both sides. I type this into the calculator and I get a new little side c of 4.911. Then I organize the information, and it's really interesting when you look at them side by side. A is the same as A. Side A, same as side A. B, same as side B. This is where the difference happens. This angle right here is the supplement of this angle. And if that's all you really want to worry about, you don't even have to draw this picture. I mean, you have to understand where it comes from, but if you just want to understand that the second triangle is always the supplement of the adjacent side, so you're given 25 and 5, so to find the second triangle, the other side, whatever it is, that angle, just subtract 180 and you can do the other problem. You don't have to draw that picture unless it helps you. Then from there, use the angle sum to find C, and then from there, you use the law of sines to find new little c. Try not to overcomplicate it. and just look at the connection between this and this, the picture, maybe the picture confuses you, but if you can subtract from 180 degrees, you can do this. 180 minus this is that, and then from there, just redo the same problem, starting with the angle sum, and then using the key ratio, and you'll get the second triangle. So a quick recap of the different cases of the law of Sine's ambiguous case before we looked at mixed examples, which will be like you would have on a test. So the first example is my altitude is so big that this side across from the angle can't touch. And again, the altitude's bigger than the side can't touch to form a triangle. Second example is the altitude is in fact the same as the contained side. You don't know that until you go through to find the altitude and you look at it, oh wow, it's the exact same number, so it must be right. And in the two triangle example, you have an altitude that allows a triangle, and then your contained side is smaller than the other adjacent side. And the one triangle example that uses the law of sines is your altitude is small enough to make a triangle, but then this is bigger and it can't fit inside. It has to fit outside, which doesn't work if it's a different triangle. So again, altitude big enough, check. Contained side small enough, 2. Contained side bigger, 1. So here are some examples, and to start off, we don't know what we have, and we're not going to actually solve the triangles here. We're just going to play the how many triangles do we have game. So you start by drawing the exact same picture every time so that you can just work through it to see if it does what you think it does or doesn't. So notice that I didn't label anything A, B, and C. I just labeled it whatever, and I always put the angle given here. Okay, and so that would be 30 degrees. And then across from that, I put 20. So there's your contained side. And then the other side, you always put here. So you get side, side, angle. And then you're always just finding the same old deal, the same old altitude here. And so the altitude, right, is always found by doing sine of the angle you're given, whatever letter it is, just put it in the left corner. And that is equal to the altitude, not the 20. The 20 is just sitting there for later. So it's always equal to the altitude right here, and then divided by the side in between, or the adjacent side, or the hypotenuse of the interior triangle, which is 10. And then the altitude is always just going to be 10, right? This side, sine of 30. And I'm going to use that to make things go a little faster for the rest of the problems. So at this point, we need a calculator or Desmos. So I went ahead and just typed it into Desmos, and we got 10 sine 30 is 5. So our altitude is 5. And so I just want you to think about this logically. If this altitude is 5, okay, is this big enough to hit the ground? The answer is yes. So there is a triangle. Now think about it logically. Can this side right here fit inside of that? Is it too big or is it just right? It's way too big. It's bigger than that. So if the triangle exists, which it does, then we look at this and see if that can then fit inside, which it cannot. So the result here is that we have one triangle. Okay, we're not going to solve for it. We're just trying to figure out how many triangles we have. All right, so the next example, it's the same picture, right? We just label it differently. So here we go. We have C, which is 30. And then here we have 10. And then here we have 20. And, you know, at some point, you don't have to draw the picture every time. You just know that the altitude, right? The altitude is equal to always sine of this angle, sine of 30, and then times the hypotenuse, so times 20. Or you could do 20 sine that, it doesn't matter. So we'll put that in Desmos as well. And so the difference is, I did write it backwards, so I'll show you that it makes the same thing. So sine of 30, and then you could say times 20 here. It doesn't really matter. You get 10 in this case. So the altitude is 10. All right, so that's the exact same thing I have here. So when it's exactly the same, you have one right triangle. And students actually do very well with that, because when they find the altitude and they see that they already have that there, it's almost no memorization required, obviously, for that example. And so the next one, just going back to the same old idea. And this is great practice to understand how to do things before you actually go through and try to find those different triangles. So if A is 32 degrees, and this is 7, and this is 10, same old deal, altitude. All right, so the altitude is equal to sine of 32 times 10, so I'll actually do 10 sine of 32. I just wanted to show you that if you understood it as sine of 30 times that, it's the same thing as doing it the other way around. Got to type that in the Desmos. So that would be 10 sine 32. Again, always make sure you're in degree mode. Horribly frustrated and try to understand something complicated like this, and you have it in radian mode. Always make sure it says degree, calculator, or Desmos. So the altitude for this is equal to 5.299, and so that gives me a triangle because the altitude is smaller than this. And so the question is, can 7 fit inside of 10? Sure enough, I mean, you can even look at it. 7 would go right there. So if the altitude confirms a triangle, and then the side that's adjacent is allowing that to go in there, meaning 7 is less than 10, then you have 2 triangles. And so this is the one you would have to, do twice, find the supplement, and then do all the calculations 2 separate times. So here's our last example. Here I just randomly made up letters. Okay, so we have an H now. H is 42 degrees. Across from H is little h, which is 12. Here we have 18, and we're trying to calculate the altitude. So to do that one, the altitude would be, again, same rigmarole. We're ignoring this unless there's a triangle. We always use the 18, and then sine of 42 degrees. And then we get out Desmos or a calculator, and we type in 18 sine of 42 degrees, and that's 12.044. So the altitude is 12.044. And now you see the no triangle example. Not by much. We did this on purpose. Just by a little bit. That altitude is too tall. So if the altitude is too tall, it doesn't form a triangle. It just, this side just kind of swings. And as you can see, if I swung that side around, it would always swing in this radius, never quite touching the ground. So this one has no triangle because the altitude is too tall. Now, if you want to work through those and actually solve the triangles, you can. Obviously not number 4, but you would use regular trigonometry for number 2. You would use the law of sines once for number 1. And for number 3, you would use it twice. And when you found this other side, so when you found side B, when you found this other angle, angle B, and you solve the triangle, that's the key. You would find the supplement of that to find new B right here. If you wanted to do that, those are some good examples to run through.